Sample size consideration for pharmacoepidemiology studies. Outline, Introduction, Sample size calculation for cohort studies, Sample size calculation for case controls, Sample size calculation for case series, and discussion. Learning objectives, examining the sample size from the investigator perspective, and calculation of the minimal sample size for cohort, case control, and case series. How many subjects should I recruit in my study? How many patients should I see? Will I have enough patients to achieve the power? How many households should I cover? Information needed to calculate sample size in the cohort studies. First variable is alpha or type 1 error. The second variable is beta or type 2 error. Third variable, minimum effect size or relative risk. Incidence of outcome in control is the fourth variable, and ratio of unexposed to exposed subject is the fifth variable. Alpha or type 1 error. It is also known as a false positive, by which one is concluding that there is a difference when in reality there is no difference. Or in other words, it's like rejecting the null hypothesis when the hypothesis is true. Most of times alpha is considered to be 0.05. In order to decrease type 1 error, or alpha, one should increase the sample size. Alpha can be one-tailed or two-tailed. One-tailed means one group is more likely to develop the disease than the other group, meaning our conclusion will be either A is more than B or A is less than B. However, the two-tailed is when both groups are likely to develop the disease. So the conclusion will be A is different from B. The second variable is beta or type 2 error. It is also known as the false negative, or when one concludes that there is no difference when in reality there is a difference. It is the probability of missing the real difference. Power is 1 minus beta. It is the complement of beta. So the probability of detecting a difference when the difference really exists is power. To increase power and decrease type 2 error or beta, one should increase the sample size.
The third variable to calculate the sample size in cohort study is the minimal effective size, also known as relative risk. In order to decrease the relative risk, the sample size should also be increased. The fourth variable is the incidence of outcome in control, meaning the disease in control. In order to minimize the outcome in control, the sample size should be increased. The fifth one is the ratio of unexposed or controlled to exposed subjects. A study has the most statistical power if the number of control, meaning the unexposed, is equal to the exposed subjects. If the number of exposed subjects is limited, so we will have an inadequate power, we should here increase the number of controls only. Doubling the controls for each exposed subject will increase the power but will not double the power. Each additional increase in the control will increase the power but in smaller increments.
We are going to talk in this section about case control studies. A case control study is a type of observational study in which the researcher selects subjects based on the presence or absence of the disease of interest and then investigates the prevalence of the exposure of interest in each study group. The approach to calculating sample size for case control studies is similar to the approach for cohort studies. Again, there are 5 variables that need to be specified: alpha or type 1 error, beta or type 2 error, the minimum odds ratio, the expected prevalence of exposure in the control group, the ratio of the number of undiseased control subjects to the number of diseased study subjects. The formula for calculating sample size for a case control study is similar to that for cohort studies. Alpha is type 1 error, beta is type 2 error, P is the prevalence of exposure in control group, K is the ratio of controls to cases, and R is the minimum odds ratio, the same 5 variables that we mentioned previously. A major limitation of case control studies is that they can require very large sample sizes to study relatively uncommonly used drugs. In addition, each disease requires a separate case control and thereby a separate study. The same case control study cannot be used to study different diseases.
A case series describes the characteristics of a group of people who have the same disease or the same exposure. The aim of this is to understand the demographics, clinical presentation, prognosis, or other characteristics of people who have a particular disease or describe something unusual. The case series method estimates the relative incidence of specified events in a defined period after a transit exposure. For example, in the Phase 4 post-marketing drug surveillance study conducted for prazosin, the investigators collected a case series of 10,000 newly exposed subjects recruited through the manufacturer's sales force to quantitate better the incidence of first-dose syncope, which was a well-recognized adverse effect of this drug. An adequate number of subjects needs to be reached to perceive an elevated incidence of a disease. This is how drug safety is founded. For the calculation, we need to adopt that the events are occurring in an extremely small frequency. Consequently, a Poisson distribution is followed. And finally, a 95% confidence interval is calculated around the observed results. On a side note, the Poisson distribution in statistics is a distribution function useful for characterizing events with very low probabilities of occurrence within some definite time or space. To make this calculation, the incidence rate must be calculated first, which is the number of subjects who develop the disease of interest during the specified time interval divided by total number of individuals in the population at risk. For example, among 1,000 patients exposed to NSAIDs during a specified time period, 3 patients developed liver disease. 3 over 1,000 is 0.003, which is the incidence rate. Moving on to the confidence interval calculations, the lower boundary of the 95% confidence interval is equal to the lower limit factor times the observed incidence rate. The upper boundary of the 95% confidence interval is equal to the upper limit factor times the observed incidence rate. The best estimate for the incidence rate is 30 per 10,000, but there is 95% chance that it lies between 6.18 per 10,000 and 87.6 per 10,000. As a simple guide known as the rule of threes is used when no events of a particular type are observed in X individuals. Then one can be 95% sure that the events occur no more often than 3 over X. For example, if 10,000 subjects are studied in a post-marketing drug surveillance study, then one can be 95% certain that any events which are not observed may occur no more than 3 in 10,000 exposed individuals, or they have an incidence rate of less than 0.003.
In the discussion, we will discuss the variables that play a role in the sample size calculation. There is only one variable that can be derived from research. In the cohort, it is the expected incidence of disease in the unexposed control group, and in case control, it is the expected prevalence of exposure in the undiseased control group. As for the other 4 variables, whether alpha, beta, minimum relative risk, or ratio of control subjects to study subjects, They are all under the control of the investigator. Therefore, the whole process of calculating sample size is an approximation. There is no reason why alpha should be specifically 0.05 or 0.04 or 0.06. Thus, these variables are chosen randomly. Usually, the investigator would search for them in the existing data, either through vital statistics, commercial drug utilization, or through studies conducted with similar population. If the investigator couldn't find data in the medical literature that are the studies, or through commercial drug utilization data sources, the investigator can pilot a study with a sample size from his population, or he can guess. What if the investigator wants to study multiple outcomes variables in cohort or multiple exposure variables in case control with different frequencies in the control group? In this case, the investigator should perform his sample size calculation based on the variables that require the largest sample size. That is of an advantage, as it will increase the power for the other outcome and exposure variables. In other words, it is preferable to have a larger sample size than the minimum to take control of wrong assumptions. If there is an important subgroup analysis that demonstrates a priori hypothesis, one should perform a separate sample size calculation for it. The investigator might perform an initial calculation, find it unrealistic, and therefore the investigator can modify the calculations to make them appropriate. Note that the discussion provided was only for dichromatous variables, that is, variables that have two options. The person either has the disease or doesn't. The discussion lacked information about continuous variables such as the weight and height. Usually, the continuous variables, they increase the power of the study if they were precise. However, pharmacoepidemiological studies, they lack that variable. Finally, there are two important issues to note about pharmacoepidemiological studies. First, it increases the sensitivity to rare adverse events due to its bigger sample size. Pre-marketing studies usually include a maximum of 3,000 participants, whereas cohort and case controls have a maximum of 10,000 participants. Second, pharmacoepidemiological studies have a problem of having a too large sample size. Therefore, it is important to analyze the results of the study. One can have statistical significance and lack clinical significance, and even if statistical significance and clinical significance was present, it might be due to the presence of confounding and bias factors.
Thank you!